Hi everyone! Today let's talk about section 13.7, change of variables in multiple intervals. So first of all, let's review the change of variable for a single variable function, and then we're gonna extend the idea. Okay? So consider the following interval, and then you can see here, wow. Inside the square root, we have 7x cubed plus 9, and then outside we have 3x squared. Well, 3x squared is kind of related to the derivative of x cubed, right? So maybe we can use a change of variable. So we use u substitution. So let u be the function inside the square root. Then du 3 times 7, 21 x squared dx. Okay, and then now because we have 3x squared dx, so how do we get 3x squared dx? Well, we can divide both sides by 7, then we get 1 over 7 du. So far so good, everybody. And then so the integral becomes, this is u of 0, u of 1, okay? 3x squared dx is 1 over 7, but 1 over 7 we can move in front. And then du at the end. We have square root of u. Well, square root of u is like u to the 1/2, right? See, we have changed the variable in terms of u, okay? And now we have a simple integral, right? We can just use the power rule. We get u to the 1/2 plus 1 is 3/2 divided by 3, and the 2 we flip it on top. Evaluate u of 0. So when we plug in u of 0, 0 plus 9 is 9. U of 1, when we plug in 1, 7 plus 9 is 16. Okay, so this is 2 over 21, and then we plug in 9. Square root of 9 is 3. 3 cubed is 27. We plug in we plug in 16 first. We plug in 16. Square root of 16 is 4. 4 cubed is 64. Okay, and so our final answer is 74 over 21. And here we're using u substitution. And you can see we changed the variable from x to u. Okay, so we change the variable from x to u. Okay, now let's continue. Similarly, some double and triple integrals can be simplified using a change of variables. So, do you remember this guy is rectangular coordinates? Okay, so if we want to change from a rectangular coordinate to polar coordinates, because here we're in two double integral, so it's polar coordinates. If it's triple integral, then we have spherical coordinates and cylindrical coordinates. Okay, so rectangular coordinate we have x, y, and so we want to change to polar coordinates theta. Alright, so this is also change of variables. Now, first of all, we need to draw what is this guy. So, what is this integral? Let's see. So we read from the outside to the inside, dx. So x is from 0 to 1. Dx is right here. And then dy. Y is from 0 to, what is y equals square root of 1 minus x squared? This is the same as y squared equals 1 minus x squared. That's the same as x squared plus y squared equals 1. Ooh, this is actually the unit circle. See? Our rectangle look like this. Okay, and because it's from 0 to this circle, actually we're only in the first quadrant. Okay, so how do we change to the polar coordinates? Well, how do our function change? Remember, x squared plus y squared is going to be r squared. So this is 1 minus r squared. And then we have r d theta. Well, theta, see the first quadrant, so it's from 0 to pi over 2. And then r is from 0, the unit circle, 1. Okay, now you see the previous functions we're not able to integrate because it's like the 1 minus x squared, we're not able to integrate. But however, after we change to polar coordinates, thanks to this r, we can do u substitution. Now we are able to integrate this function. You see this magic? Okay, so we can do u substitution. Let u be the exponent of e. So 1 minus r squared. Du is minus 2r dr. And r dr is then equals minus 1/2 du. So far, so good, everybody. Theta is from 0 to pi over 2. And then u is from u of 0 to u of 1. Okay, I will calculate what's u of 0, what's u of 1 in the next step. And then here we have e to the u. Well, r dr equals minus 1/2. We'll put it in front, du. Okay, and we also have d theta. So what is that? Well, integral of e to the u is e to the u. And then u evaluate from u of 0. So we plug in r is 0. So 1 minus 0 is 1. We plug in u of 1. So 1 minus 1 is 0. So what is that? That is, we plug in 0 first. We have e to the 0 is 1. Minus, when we plug in 1, we get e. So this minus, we can actually distribute it. Then we have e minus 1, and then times 1/2. And integral of 1d theta is just theta, evaluate from 0 to pi over 2. So this is the same as we multiply by pi over 2. Because when we plug in 0, it's gone. So this is e minus 1 times pi over 4. Okay, so this is the double integral. Okay, that's the volume under this surface. E to the 1 minus x squared minus y squared. So far, so good, everybody. So you can see we make change of the variable. Actually, we change it twice. We first change to r and theta, and then we use u substitution. Okay, let's generalize this idea. Okay, transformations in the plane. A change of variable in double integral is a transformation that relates two sets of variable, u, v, and xy. Okay, so t is a transformation. It's from r2 to r2. Okay, so we have xy equals t of uv, so that equals x of uv, comma y of uv. So far, so good, everybody. Okay, next, the Jacobian determinant of a transformation. So given a transformation t uv equals x uv y uv, where the component functions are differentiable on a region of the uv plane, then the Jacobian determinant of t equals j of uv equals the partial derivatives of xy with respect to uv. What does that mean? Well, that means you take the partial derivative of x with respect to u. You take the partial derivative of x with respect to v, and then you take the partial of y with respect to u. Take the partial of y with respect to v. Then the determinant is cross multiple, but subtracts. So partial x, partial u, partial y, partial v, minus partial u, partial v, partial y, partial u. Okay, a transformation T from a region S to a region R is 1-to-1 on S if T of P equals T of Q only when P equals Q. So when P, Q are points in S. So what does that mean? Let me draw some picture here. So suppose we have XY plane and we have some region there. And then we want to use the transformation T. And then now our new set of variable is U and V. And what we want to do is, you know, this is a region. Okay, we want to, through this transformation, we want to get it mapped to a rectangle. You know, so here before we have a double integral of f dx dy or dy dx on this region R. Oh, let me see, from region S to R. Oh, okay, so let me call this S. Okay, so S is a region in the XY. Okay, so then R is this region get mapped to on the UV plane. Okay, so this is on S, and then after we change of the variables, we get so this is a change of the variable for double integrals. Okay, so given a transformation T where the component functions have continuous first partial derivatives, suppose T maps a closed region S in the UV plane onto a region R in the XY plane, and T is a 1-to-1 on the boundary of S, then if F is continuous, okay, so sorry, my arrow is a little bit different. Okay, so the arrow is this way. Okay, it maps from a closed region in the UV plane. Okay, so this is S mapped to R, the region R on the XY plane. Okay, all right, then suppose T is 1-to-1 on the interior of S. Okay, if F is continuous on the region R, then we have the double integral on the region R. So this dA is either dx dy or dy dx. Okay, that equals the double integral over the S, the region S in the UV plane, f of x UV comma y of UV, and then this is the absolute value of the determinant. So determinant is this expression, and it's a number, okay, or is a function, okay. Then we can consider the absolute value of that function, and then here dA is either du dv or dv du. So far so good, everybody. So let me draw a picture. So you know f is a function from R2 to R. Okay, so the input is xy and then the output is z. Okay, so the picture is like on the xy plane we get a surface, something like that. Okay, and what does T do? So T is from R2 to R2. So we change a variable UV. Okay, so now this guy, this composite function f composite T now is a function from the UV plane to the space. So now we have a UV down there and we have the Z down here. This is F, but now we have maybe a different surface, but now we want to restrict so that our UV is a rectangle. A rectangle is much easier to calculate. Okay, so it's much to calculate in this case. And this surface is F composite T. So far so good, everybody. So that's why T mapped the U from the UV plane onto the XY plane. So far so good, everybody. Okay. With this picture in mind, let's do the following exercise. Okay, so let's check dx dy equals r dr d theta. What is it talking about? So we have the xy rectangular coordinates, and we want to change to r and theta, that is the polar coordinates. And we want to express x as a function of r and theta, and we know that x equals r cosine theta, and y equals r sine theta. Okay, so we want to compute the Jacobian determinants. Okay, so what's partial x partial r? Well, to the derivative with respect to r, we have cosine theta. What is partial x partial theta? Well, the derivative of cosine is minus sine. What's partial y partial r? Oh, that's sine theta. What's partial y partial theta? Well, that is the derivative of sine is cosine theta. Now, the Jacobian determinant equals, well, the determinant of those four functions. So let's put it in the right place. Okay, now what we're doing, we cross multiply by subtract. So you can see we have r cosine square minus r sine theta squared, but because of the negative, it becomes positive. Yes. And we can factor out r, we just get cosine squared plus sine squared, and the factor cosine squared plus sine squared equals 1. So that's why we get r. Okay, so that is why dx dy equals, so if we have an interval of f on r is on the xy plane, and let's say S is the region in the polar coordinates, then we have the f, and then in terms of r and theta, and the Jacobian is r, and then we have the r d theta. So far so good. So this guy is in fact the Jacobian. So far so good, everybody. So now we have verified that. Let's continue to do some examples. Yeah, we love examples. Okay, so let's look at this example. Evaluate the interval over the region R. So R is a parallelogram in the xy plane with vertices 0, 0, 0, 1, 2, 4, and 2, 5. Okay, so here, suppose we're not given the transformation. How can we think about that? First, let's draw some picture. Okay, so we have let's say 1, 2, 3, 4, 5, 0, 1, 2. Okay, so the parallelogram, so this is the xy plane. We have 0, okay, 0 and 0, 1. Then we have 2, 4. So sorry, this is 1, 0. We need 0, 1. Okay, 0, 1 is right here, and then 2, 4, and 2, 5. Okay, this is the parallelogram. Okay, so what are the boundary functions? Okay, so first step, figure out the boundary functions. Because 2-point fixed line, all those segments, we can use line to represent, right? And let's look at, let's see this one. We know the line y equals mx plus b, and here the b equals 0. Okay, okay, let me put what we think here. So the first line, b equals 0, m is the slope. So that is change in y over change in x. So this is 4, right? 2, 4. So y is 4, and the x is 2. The other point is 0, 0. Oh, so we get that's 2. So that line y equals 2x. So far so good. How about this top line? Well, it's the same slope. We just move up 1 unit. So y equals 2x plus 1. So far so good. How about this guy? Well, this is a vertical line, right? Vertical line, and this is like x is 0. And then this guy is x equals to 2. Now we have figured out the 4 boundary functions. Okay, second steps. Express the boundary functions as f of xy equals constant. G of xy equals constant. Okay, let's see how can we do it. Well, we can let's see this guy. We can move the 2x on the left. We get y minus 2x equal to 0. This guy is already left hand side is x, right hand side is a constant. This guy is already good, right? And then this guy we can change to y minus 2x equals 1. So now the 4 boundary functions give us y minus 2x equals 1, y minus 2x equal to 0, and x equals to 2, x equals to 0. Okay? So you can see this guy are the same, this guy are the same. Right? So the next step, let u be y minus 2x. Let v be x. So it depends on which one. So this guy and this guy. So let it be the new variable u and v. Then now, what happened? The first guy. So this guy is correspond to u equals 1. This guy is correspond to u equals 0. This guy is correspond to v equals 2. This guy is correspond to v equals 0. So you can see now u and v, the boundaries, they're just constants. So I can draw a picture. This is the uv plane. Okay, the uv plane. And now what happened? U is from 0 to 1. V is from 0 to 2. Now you see? Okay, so wow, this is much easier. We just get a rectangle, right? Okay, now next we want to figure out the Jacobian determinants. So we want to express x and y in terms of u and v. So step 4, express x and y in terms of uv. Okay, so how do we do it? Well, we have u equals y minus 2x, v equals x. Oh, so x equals v. And then let's solve for y. So y equals 2x plus u, right? We move the 2x on the left. and then x is just v, so this is u plus 2v. This is the y. So far so good, everybody? Okay, now let's see. What is, so 5, compute the Jacobian. So partial x partial u equals 0, partial x partial v equals 1, partial y partial u is 1, partial y partial v is 2. So the Jacobian is the determinant of 0, 1, 1, 2. 0 times 2 is gone. Minus 1 times 1 is minus 1. Oh, you may notice that our transformation and the problem given a little bit different. What they do is they let this guy be 2u, they let this guy be v, but anyway will work. Okay, the transformation, our idea is to have a rectangle, okay, on the UV plane. So you can switch to U or V, or you can scale. So under the transformation that the problem suggests, we will have a square on the UV plane, and they both start with 0 and end with 1. Okay, but it's okay, we can continue with our transformation. Okay, so by the way, different transformation, the Jacobian determinant might be different, but however, the answer at the end, okay, will be the same. So let's continue. Let me see, do I have enough space here? Okay, so let's set up the integral. Okay, so the integral, now we have the f. So square root of 2x. What is 2x? So that's 2v. Y minus 2x is u. Okay, dA is determinant of is the absolute value of the Jacobian determinant. And then we can, because now it's a rectangle, so du, dv, and dv du, they're just the same. So here v is from 0 to 2, u is from 0 to 1. Okay. Now you can see the absolute value of minus 1, this guy is just 1. And then, so we can pull out the square root of 2 outside. And then we have u to the 1/2, v to the 1/2, du dv. So let's see. Integral with respect to u, so u to the 3/2 over 3 times 2 times v to the 1/2, and u is from 0 to 1. Okay, so 0 to 1, we plug in 1, we get 2 over 3. When we plug in 0, it's gone. And then integral from 0 to 2, v to the 1/2 dv. So 2 root 2 over 3, we get v to the 3/2 over 3 times 2. Now evaluate from 0 to 2. Well, when we plug in 2, we have 2 square root 2 and then cube. This is like 2 root 2. And then we have 9 at the bottom. And then when we plug in 0, it's gone. So let's see. This root 2 and this root 2 give us a 2. So then it's like there are 4 of 2 multiplied together. 2 to the 4th is 16. So the answer is 16 over 9. Okay, so you can also check. So check at home. Okay, after class, check at home with the transformation that the problems suggest. We should have the same answer. Okay. All right. Let's continue. So when do we use the transformation? Usually when we see like 4 boundary functions and they're like kind of similar. I mean, the two different sides, they are similar to each other, and then we can think about the transformation. We can map this region to a rectangle. Okay, so yeah, in the UV plane. Yes. Okay, so we evaluate the following integrals. So where R is the parallelogram in the xy plane with the vertices. Okay, yeah, so when we see a parallelogram, yeah, we think about the transformation, because we can easily change the parallelogram into a rectangle. Okay, so let's see, it passed through 0, 0, 1, minus 1, 2, 0, 1, 1. Okay. All right, so what is the first step? Well, figure out the boundary functions. What are boundary functions? Okay, let's see. This one is easier. This is the slope is just 1, right? So, and the y-intercept is 0, so y equals 1. And then, sorry, y equals x, I mean. And then how about this line? Well, this line, when we extend it, we know it intersects at -2. So this is y equals x minus 2. Okay, and this guy is y equals minus x. And then here, when we extend it, we know it intersects at 2. So this is y equals minus x plus 2. Okay, now look at the 4 boundary functions expressed in the form of some function equals a constant. Let's see, how do we do that? Well, here we can move the x on the left, and then we have x plus y equals 2. Right? And then here we can move the x on the left, and we have x plus y equals 0. So far so good. Here we can either move move the y on the right, or we can move the x on the left. Just up to you. No matter which choice, we will get the same answer for the integral. Maybe the transformation could be different. Okay, so let's do x minus y equal to 0. Here we will have x minus y. So move the y to the right, it become negative. Move the -2 to the left, it become positive. So far so good, everybody? So now let's see, how do we do it? So we can do transformation. You see these two guys, they are x minus y. So we can have u be, let u be x plus y. So let u be x plus y. Let v be x minus y. Okay, and then u now is between, so here this corresponds to u is 0, this corresponds to u equals 2, so u is from 0 to 2. And how about v? This is v equals 2, this is v equals 0. V is also from 0 to 2. This is on the uv plane. So far so good, everybody. So our transformation mapped the region on the UV plane to the region on the XY plane. In the XY plane. Okay, next we want to compute the Jacobian. So we need to express x and y in terms of u and v. Here we have a system of equations. Right? How do we do that? Well, we can use equation 1 plus equation 2. Then the y cancel, we get 2x equals u plus v. So x equals 1/2 u plus 1/2 v. And then we can do equation 1 minus equation 2. Then we have 2y equals u minus v. So y equals 1/2 u minus 1/2 v. Okay, So this is our transformation. Now, what is the Jacobian? So partial x partial u is 1/2. Partial x partial v is 1/2. Partial y partial u 1/2. Partial y partial v is minus 1/2. Then the Jacobian equals the determinant 1/2, 1/2, 1/2, minus 1/2. So it'll be it's 1/2 times minus 1/2, so minus 1/4 minus. So cross multiply, right? 1/2 times 1/2, which is 1/4. So minus 1/4 minus 1/4 minus 1/2. Okay, finally. This is the integral. Okay, what is the function? Well, x minus y. X minus y, look at this. X minus y is v. And then x plus y is u. Okay, dA becomes absolute value of Jacobian determinants, and then because now it's a rectangle, so du, dv, or dv, du doesn't matter, and they both from 0 to 2. So far so good, everybody. Okay, let's see. So here, absolute value of 1/2 is 1/2. We can move it in front. Then this is like v to the 1/2. And then this is u plus 1 to the minus 1/2 du dv. Well, here we're gonna do u substitution. Abuse of notation. So let's call it w substitution. So let w be u plus 1, and then du equals dw, right? Then let me pause this. Okay, so this is 0 to 2, and then here we have w of 0, w of 2, v to the 1/2 still there. This is w to the minus 1/2, du is dw, dv. Okay, now let's see what it is. V to the 1/2 stay there. W to the minus 1/2, we add 1, we get w to the 1/2, and then divided by 1/2 is the same as times 2. Evaluate. What's w of 0? Well, u is 0, so 0 plus 1 is 1. W of 2, 2 plus 1 is 3. dB. So 2 cancel. V to the 1/2, and we get square root of 3 minus square root of 1. So pull the constant out in front, and then this is v to the 3/2 over 3 times 2. Evaluate from 0 to 2, so we plug in 2. Plug in 2. Here, square root of 2 and then cube it. So this is the same as 2 root 2. And then when we plug in 0, it's gone. So that's why we have root 3 minus 1 for root 2 over 3. So this is the final answer. So far so good, everybody. Okay, so you can also try to maybe try other transformation. Maybe you can let u be y minus x, let v be x plus y. And then you can calculate to see whether you have the same answer. Okay, so when you if you see a parallelogram after you draw it, then think about the transformation. Okay, change of the variables. All right, let's continue. Okay, so the boundary functions are not necessarily lines. Okay, they could be curves, but the two curves there, we should see two pair of curves. one pair is like a function we shift a little bit, and the other pair is another function we shift a little bit. Okay, so let's see here. Evaluate the integral, the double integral of y squared dA, where R is the region in the first quadrant, bounded by the parabolas. Let's see. Okay, let me draw the picture. First quadrant, okay, so x equals y squared. Oh, and this problem, the boundary function are already given. So x equals y squared is like that, right? X equals y squared minus 4 is the same shape. We shift down a little bit. 9 minus y squared. Let's say 9 here, 16 there. Then it's something like that. Here is something like that. So we're talking about the region in the first quadrant. So far so good, everybody? Okay, now let's figure out each boundaries. And because we're already given the boundary functions, let's express as a function of xy equals constant. Okay, let's express in this form. Well, this guy is on the x equals 16 minus y squared. So x plus y squared equals 16. Okay, then this guy is x plus y squared equals 9. This guy, x equals y squared, so x minus y squared equals 0. This guy, x minus y squared equals minus 4. So far so good? Do you see the two pair of functions? Now, how do we set it up? We can set up the u. So we can set up the u to be x squared plus y squared. Oh, sorry, x plus y squared. Okay, it's like this guy and this guy. Okay, so then this is like u equals 16. This is like u equals 9. And then we have v be x minus y squared. And then this is like v equals 0. This is like v equals minus 4. Then how do we draw it on the u, v plane? U is from 9 to 16. V is 0, negative 4. Oh. So this is the rectangle. So far so good, everybody? Okay, let's see. Next steps, we want to express x and y in terms of u and v. So how do we do that? So how do we get the x? We can use equation 1 plus equation 2. Then we have 2x equals u plus v. So x equals 1/2 u plus 1/2 v. And then how do we get the y? We can use equation 1 minus equation 2. Then we have 2y squared equals u minus v. Y squared equals u minus v over 2. But y is plus or minus. Okay? But because our y is, our region, the y is positive. See, that's why we have the two regions. One is in the first quadrant, one is in the fourth quadrant. And now we pick the positive one. So that is the square root of u minus v over 2. So far, so good, everybody? Okay, what is that? Well, that's the same as square root of 2, and then so 1 over square root of 2 times u minus v to the 1/2. Okay, because next step we're gonna differentiate, okay, and find the Jacobian. So let me copy it down right here. X equals 1/2 u plus 1/2 v. Y equals 1/√2 u plus v to the is it u minus v? Okay, yeah, u minus v. Okay, so this problem is more complicated than our previous examples because now the boundary functions are curves and they're not lines. Okay, so partial x partial u is 1/2. Partial x partial v is 1/2. This is easy. But partial y partial u, chain rule. So chain rule 1/2 u minus v to the minus 1/2 times derivative with respect to u is 1. Okay, so this is 2√2 and then u minus v to the 1/2 means they're in the denominator. So far so good, everybody? And on the other side, dy dv is 1/√2 chain rule 1/2 u minus v to the minus 1/2. Derivative with respect to v, we get a minus 1. So this is negative 1/2√2 u minus v to the 1/2 down there. Okay, Jacobian. 1/2 1/2 1/2√2 u minus v to the 1/2. They're negative 1/2√2 u minus v to the 1/2. Cross multiply, we get minus 1/4 square root of 2 u minus v to the 1/2 minus same thing. Yeah, 1/2, 2√2 times 2 is 4√2 u minus v to the 1/2. This is the same as negative. Get to the 2 copy, 2 and 4 cancel, we get 2√2 u minus v to the 1/2. Whew, okay. Finally, our integral y squared. What is y again? Oh, this. So it's 1/2, and then u minus v to 1/2 squared. The 1/2 and square cancel. Jacobian. The absolute value of the Jacobian. Well, that is 2√2. Because the minus is gone, and then we have u minus v to the 1/2 du dv. Because we have a rectangle, the order of du dv or dv du doesn't matter, but the outside is v. V is from 0 to minus 4 to 0, and the u is from 9 to 16. Pull out the constants for √2, and do you see what happened? This is u minus v to the 1/2. So far, so good, everybody? Okay, so how do we calculate that? We are doing u substitution. We should call it w substitution. Okay, so w is u minus v, but here we first consider u is the variable, v is a constant. So u is the variable, v is a constant, right? And so dw is 1 du. Okay. Then here we have interval w of 9. Okay, let's see here. In this problem, I suggest we calculate and then express our answer in terms of u and then plug in the u bounds there. Okay, so this is like integral of w to the 1/2. When we integrate it, we get w is u minus v to the 3/2 over 3 times 2. That we can do that because dw is 1 du. Okay, now we plug in u is from 9 to 16. Okay, so 2 over 3, stay there. Put in outside. We plug in 16 first. 16 minus v to the 3/2 minus 9 minus v to the 3/2 dv. So far so good, everybody? Okay, let's see. That equals 2 root 2. See, the 2 and 4 cancel, so we have 2 root 2. Oh, times 3, the 6 root 2. And then, oh, here we're gonna do, we're not a variable, another u substitution. W, and we have used x and y already. Which variable do we use? Let's use t. Okay, so you can, or you know, the thing is here you're gonna do it like, let's look, s substitution and let s be 16 minus v. Here you're gonna do a t substitution, let t be not minus v. So I'm not sure whether you're familiar with the u substitution in our brain. Okay, it's the u substitution, but because there are so many s and t, let's omit the details, and then we can calculate it directly. Okay, so first guy, think about if s equals to this, ds will be minus dv, right? So we have this guy, 16 minus v, we add 1 to the exponents, that is 5 over 2, divided by 5 times 2, but we should multiply by minus 1 in order to create a negative dv. Okay, and then we have minus 9 minus v, add 1, we get 5/2 over 5 times 2, but we also need to multiply by minus 1 because dt equals minus dv. So far so good, is that okay? If you like, you can try to write out the details, okay? And now let's see what happened. So here we plug in 0 first. Oh, 0. Then we get square root of 16 is 4. So 2 times 4 to the 5th over 5, and it's negative. Next, we have minus become plus. And then we plug in minus 4. 9 minus negative 4 is like 9 plus 4, 13. 13 to the 5/2 over 5. So far so good, everybody? Oh, we forgot some terms here. So let's see. Oh, we should first plug in 0. Oh, that's what happened when we have so many terms. We should first plug in 0, and this is what happened when we plug in 0. And then this guy, when we plug in 0, we get 9 to the 5 over 2. Then square root of 9 is 3, right? 3 to the 5th. And then we should subtract when we plug in minus 4. Okay, so here minus negative, and we have 16 minus negative 4 is like 20, so that is 20 to the 5/5, and here minus become plus. 4 plus 9, 13 to the 5/2. Okay, what is that? Ooh, so that is, this is negative 2, 4 to the 5th, 5, plus 2, 3 to the 5th, 5, plus 2, times 20 to the 5 half, 5 minus plus become minus 13 5 half over 5. So far so good, everybody. Okay, so plug this in your calculator. And what do you get? So I get approximately equals to 18.79. So please plug in your calculator and see whether you have the same answer. Okay? Because sometimes I might make mistakes. You might have seen that before. So that's why everybody could make mistakes. So we learn from our mistakes. So check carefully after we're done. So I really hope that after you finish your exam, don't just hand in your exam. Go back and check your work if you have like some time left after you finish. Okay, so check a couple times before the time is over. So far so good, everybody. So today we talk about change of variables, and it's useful when the region on the xy plane, the boundary functions is not like a rectangle or it is like some curves, two pair of curves. Okay, then think about the transformation, change of variables. That's finished our chapter 13. So please do your homework and the practice exam, and if you have questions, feel free to ask me. Cheers! Bye!